Hello, in this video, we will use LINEST to perform the logarithmic regression analysis of this dataset, which is in the logarithmic form. So the logarithmic form or logarithmic equation of this dataset where we have y equals b0 plus b1 ln x. In the matrix form, we factor out b0 and b1 as a separate matrix. It becomes 1 comma ln x or 1 plus ln x times the matrix b0 and b1. b0 and b1, we will calculate that value. b1 ln 1 and ln x will be the transformation of this dataset. So we begin with the equation from the chart, the scatter chart. Where we convert this to scatter chart and customize, where we show the logarithmic equation as label. That's logarithmic, and we show it as label. So the logarithmic equation is 0.132 plus 11.9 ln x. So that's the equation. So this is 0.132 plus 11.9 times ln x. So that's the equation of our y, where we will calculate these coefficients b0 and b1 using LINEST function and the matrix function. We will also show the r squared value. From the chart, we have the r squared value. We show the r squared value. Our r squared value is 0.64. We will use the LINEST to verify these values and the matrix operation. We begin with the transformation of the dataset, where we have 1 plus ln x. So we have the 1 column and the ln x column, which is RA formula, ln of the x values. Now that we have the 1 ln x matrix, we can now calculate or the LINEST or use the LINEST function, where you have data y and data x, and we'll show the full statistics. Here you have 10 outputs, and you'll notice the value b1 is 11.64, and it is 11.9, which is rounded off. The value of b0 is 0.1317, and it is rounded off as 0.132. The value of r squared is 0.64029, and r squared here is 0.64. We will use the matrix. But before we do that, we can use the slope function, because we have already transformed the data to the linear form, where we have data y and data x. 11.6864 matches to our LINEST output. We use the intercept of data y and data x. And this matches to our LINEST output, as well as these coefficients matches to our LINEST output and the equations of the chart. We can also calculate the r square, which is rs cubed of data y and data x, which is 0.6402, matches to our LINEST output and our chart. Stay x, we can also calculate stay x. Again, data y and data x. And this matches to our Linus output. We can calculate the degrees of freedom because it is rows of the dataset range of the dataset range minus columns of the dataset range of dataset range. And that is 7 matches with our Linus output. And residual sum of square, which is equal to uh, DFD, degrees of freedom of denominator, times stay x to the power 2, or stay x squared. 271.11 matches to our Linus output. And our ESS, which is equal to, first we calculate the population, which is rows of the dataset range. We have 9. And our ESS equals RSQ times N times variance of the population Y, or the independent variable. 482.595 matches to our Linus output. Now we can calculate for the F statistic, which is equal to ESS divided by the number of independent variable. We have only one for x, so we write here 1 divided by stay x squared. Stay x to the power 2. 12.46 matches to our Linus output. Now we'll calculate for the this last two standard error value estimate. We start with the Pijarina inverse matrix, which is minverse and mult transpose of this matrix, the 1x matrix, and itself. Now we can calculate for the standard error value of the intercept, which is equal to stay x times square root of the Pijarina red. That's 5.107 matches to our Linus output. Then standard error value of the B1, which is equal to stay x times square root of Pijarina blue. And this 3.36 matches to our Linus output. And we can continue solving for the coefficients, which is you calculate the Pijarina cofactor, which is M mult transpose of this matrix and the y values. Now that we have the cofactor and the inverse, we can calculate for the coefficient, which is equal to M mult of the Pijarina inverse and the Pijarina cofactor. So our answer for B0 is 0.1317, matches to our Linus output, and the equation 0.132, and 11.86 B1 matches to our Linus output as well as our chart equation. This completes our Linus function for logarithmic regression.